Somebody help me. I don't understand the inductive effect. It just doesn't make any sense. Don't worry, I'm here to help. Let's jump into it. Okay, we're talking about anti-Markovnikov brominations of alkenes in chapter 25. But first, we've got to go back in time to chapter 11. Whenever we talked about this earlier, but this time it was Markovnikov. So I'm just going to give you a quick recap of that mechanism. The alkene, pi electrons, will attack this hydrogen and move or create a bromine anion. There we go, that's the word. Anyway, that carbocation is obviously more stable here. It's okay, I'll explain it. Instead of here, which means that the bromine is only going to attack here, making the rich get richer, or the carbon that already has more carbons attached to it, the secondary instead of the primary, the secondary will get the prize, the bromine. Awesome, great job. So in anti-Markovnikov, we're going to be dealing with radicals, spoiler alert. And the question I want to be asking is, what would stabilize a radical? A radical being just one single electron instead of a pair of electrons on an atom. So what would stabilize a radical, which is just one electron instead of two? Okay, but first, quick explanation of the inductive effect, which is really just electronegativity of atoms, and whether or not they are electron releasing or electron withdrawing. And so, for instance, carbon, not very electronegative, which means that it's going to be actually pushing electron density away from itself. Vibe check. I don't want those bad vibes. I'm out. Fluorine loves bad vibes, apparently, if we're continuing the metaphor, because it's electron withdrawing, means it's withdrawing the electron cloud away from the molecule and towards itself. And so, if we're talking about the eventual chain that's going to have our radical on it after the alkene bond breaks, if it has a single electron on it, and we're trying to find if it's going to be Markovnikov or anti-Markovnikov, trying to decide where it's going to bond or where this bromine or whichever is going to add, what do you think is going to stabilize this radical? Something that is pushing electron towards it or drawing electrons away from it. And not necessarily even that, but just the difference between primary and secondary being that one will push more and one won't push as much. So go ahead and take it. I won't make you think about it. I'll just tell you. Here we go. It's going to be secondary because this has one carbon pushing electrons towards it and another. And the thing that would stabilize a radical is having a buddy. It just wants a pal, a friend, to be alongside it. So the thing that would stabilize it would actually be a second electron. And so if it was primary, it would be way more by itself. You know, it wouldn't have as much of the electron density being pushed towards it. It'd be more isolated. And so similar to a carbocation, like in the example of Markovnikov, the radical is more stable on the more substituted carbon. Welcome to the chain gang. Yeah, what's up? That's what radicals say, basically. That's what they are. And in anti-Markovnikov equations, obviously we're dealing with radicals, which is, pretty tight stuff, going on. Peroxide, hit me up. There's three things you're really going to need to know is that we're dealing with initiation steps, propagation steps, and termination steps. You fade. That's right. Trump 2022, am I right? Or 20... I don't know. I'm not talking about politics right now. Anyway, another thing we're going to be doing is we're going to be using the half arrow instead of the full arrow. I can't point to it. And we're going to be using something called a radical initiator to really get us started. And so the most pumped and excited and wacko radical initiator out there is peroxide because he's a cool homie. So we're going to be dealing with my little peroxide boy right here. Notice I'm using the half arrows to draw that the radicals are actually forming because that splits apart. So just great job, peroxide. Thank you for kicking us off. So this is going to attack hydrobromic acid, and a bond is going to reform when one of the electrons in this bond leaves. It says, psych, I don't want you, I'm out, and this electron has to settle. It's got to settle down. And so you can see, I just want to, spoiler alert, this bromine right here and this bromine right here are reformed, and it has sort of this chain reaction propagation steps where the starting reactant and the ending product are reformed over and over. And so this will continue to happen over and over again until the reaction stops. So we have our initiation step where the radical is started, and then these propagation steps are sort of the things that keep the reaction going, and in the end, we might have some termination steps that will actually stop it. So don't look over here yet. Don't do that. Stop. We're going to have one of the pi electrons from the alkene form another bond with the radical and move the radical here. Now, we already talked about why that's so stable. Great job. You were listening the whole time, I bet. And we're going to have this radical on the chain now, attack hydrobromic acid again, reform that bond with the hydrogen, and again, the starting ending product is reformed the same as the starting product. So this is going to keep going over and over again in these things called propagation steps. Now, some of the termination steps that can form are when two radicals interact with each other and kind of cancel out. So sad chain gang is no more, chain reaction gang. So an example of that would just be bromine gas forming if this were to bond with itself, or if this were to bond with itself, or if the two were to combine, like so. But again, those are not major products, they're pretty minor because of this cycle where the hot potato radical just keeps getting passed around because he's just really excited. He's just really glad to be out there. He wants a partner though, we gotta supply that. Gotta help your fellow radical men out, or women, whatever. It's cool. So there you go. You have Anti-Markovnikov edition. Hopefully, the makes 100% sense to you. Hey, so I just wanted to mention the last couple things that I didn't mention in the other videos that I was rewatching them. I was like, hey, I should just clear some things up real quick. First thing is that this is the product that's formed. I never actually said that, but it's important that in those propagation steps to actually identify what the product is that's being formed and being taken out of those propagation steps as they continue to use up all the reactants. There is actually a product that's being formed. I didn't actually mention that. Second thing I thought that was kind of neat about this mechanism specifically is that this doesn't have a charge. That's kind of a neat thing that we've never seen before, is a halogen that doesn't have a charge, because its octet isn't full, but it's the number of protons that it has is completely neutral compared to the valence electrons. So kind of a neat thing to think about as well. And another thing that I don't like is when people just show the mechanism example that's given in the book, and that's kind of the one that I followed. But just real quick, if we're thinking about what an example problem might be of trying to figure this out, if we had something that looked like this, which is a little more complicated, a little more complex with HBr and peroxide, we would know that the peroxide means that it's going to be anti-Markovnikov. So the bromine addition is going to be at the less substituted carbon, because we're not dealing with a carbocation that needs to be stabilized. Now we're dealing with a radical that needs to be stabilized. So instead of the hydrogen being added first, now the bromine is actually being added first in the mechanisms of the Markovnikov versus anti-Markovnikov. So a neat thing there. If we were to actually carry this out, the bromine would add to the secondary instead of the tertiary. So just notice if you're dealing with peroxide or not, the actual mechanism, if you're writing it out just for a synthesis problem, is actually written the same, just one has peroxide and one doesn't. So this is just a super quick thing to remember in your mind is if you're having an alkene and you want to brominate it, whether or not you have peroxide in it dictates whether it's Markovnikov or anti-Markovnikov. Thank you so much for watching.